Pressing a key to execute a command feels instantaneous, but human intent is chaotic, and machine logic is rigidly binary. Closing the architectural gap between a human at a keyboard and the physical routing of light through fiber optics requires a strict sequence of translations. The OSI model provides the framework to bridge that gap. To understand software communication, we isolate the highest levels, layer 6 and 7. Layer 6, the presentation layer, is the syntax boundary, managing data compression, encryption, and translation between character codes. Sitting at the absolute top is layer 7, the application layer. This is the direct human-computer interaction boundary. It identifies communication partners, dictates resource availability, and selects the specific protocols required for the task. Because layer 7 sits at the top of the stack, it serves no other layers. It relies entirely on the transport and all layers below it to execute the physical communication across the network. Executing a network request requires a strict sequential bootstrapping process. The system must acquire an identity, resolve addressing, secure a channel, and define payload logic before a single byte of user data achieves its purpose. Before any application can function, the localized host machine requires a globally routable IP identity. This diagram shows the Dynamic Host Configuration Protocol, or DHCP. It dynamically assigns identity, preventing IP conflicts. The client broadcasts a discover query. The server replies with an offer. The client issues a request, and the server sends an acknowledge, granting the temporary identity. With an identity established, the system initiates the second phase of bootstrapping, translating a human-readable alphanumeric URL into a 32-bit numeric IP address. Here we see the architecture of the domain name system, or DNS. The DNS resolver first queries the root server, which directs it to the top-level domain server. The TLD server points the resolver to the authoritative name server, returning the final IP address. This flowchart models a recursive DNS service. Here, the resolver passes the query burden entirely down the chain, communicating only with the root, which recursively requests the data from the remaining servers. Contrast that with this diagram of an iterative DNS service. In this model, the resolver acts as the central hub, communicating directly and independently with each tier of the server hierarchy. By handling this translation seamlessly in the background, DNS abstracts the mathematical rigidity of network routing, enabling a universally standardized human-navigable internet. Data routed via IP and DNS remains exposed to modification and interception at every transit node. This model illustrates where Transport Layer Security, or TLS, sits in the network stack. It operates just beneath the application layer to provide data secrecy and server authentication. During connection, TLS uses a client-server handshake mechanism. The devices exchange digital certificates to prove identity, followed by a session key exchange using public and private asymmetric encryption infrastructure. The architectural placement is strategic. TCP-based applications avoid constructing complex security features because TLS encapsulates their messages inside cryptographic packets before handing them off. Layer 7 protocols like HTTP depend entirely on Layer 6 TLS encapsulation to guarantee their integrity across untrusted networks. The final barrier before application delivery is format incompatibility. Early protocols like SMTP were originally limited to transferring only 7-bit ASCII characters, making images and video impossible to send directly. This diagram maps the MIME protocol, designed to bypass character limitations of simple mail protocols. MIME parses complex digital content into transmittable 7-bit ASCII code. When data reaches the recipient, MIME executes a reconstruction phase, translating the ASCII back into the original multimedia format. The presentation layer ensures that lower-level transport protocols never have to process or even understand the complex multimedia payloads they carry. Within the application layer, protocol design is dictated by the specific delivery requirements of the data. This schematic outlines the File Transfer Protocol, or FTP. To maintain state across disparate systems, it establishes two channels. First, the control connection remains connected during the session for rule communication and authentication. Second, the data connection opens exclusively to transfer the file payload. This dual-channel split allows Layer 7 to handle uninterrupted heavy data transfers alongside ongoing administrative commands. Unlike the live connections required by FTP, Email uses asynchronous communication. The sender and receiver are almost never online simultaneously, demanding a decoupled architecture. Look at this model of the Simple Mail Transfer Protocol, or SMTP. It acts as the exclusive push mechanism, operating over TCP port 25 to send outbound messages. SMTP delivers messages to the destination server's queue, but it lacks the architecture to interface directly with the end user's offline inbox. This process diagram shows the Post Office Protocol, or POP3. This acts as a localized pull mechanism that downloads the payload to the user's device and immediately deletes the copy held on the server. Alternatively, this diagram depicts the Internet Message Access Protocol, or IMAP. Operating on port 143 or the secure port 993, IMAP synchronizes state and manages remote mailboxes, allowing users to access messages without forcing a local download. Maintaining a modern inbox requires a fragmented, highly orchestrated ecosystem of independent delivery and retrieval protocols acting in concert. Every network request requires this complete sequence: acquiring localized identity, resolving global addressing, establishing secure cryptography, and deploying specialized application mechanics. The upper OSI layers function as highly specialized modular toolkits, providing the specific instructions needed to map human intent onto machine logic. Ultimately, layers 6 and 7 exist solely to map chaotic human operational logic onto rigid, stateless digital infrastructure. Network engineering centers on architecting the translation protocols that make raw packets usable to humanity.